So we've just covered sedimentary rocks, and the next stop along the way is to talk about some key geologic principles. Now, these were actually discovered by studying sedimentary rocks, and yet we use them throughout geology, so it's kind of important this way. These key geologic principles, kind of stretch back all the way to the earliest scientists who were studying the galaxies. And well, there were no galaxies back then, but there was the universe as they understood it. And some people felt that the sun was the center of the universe, and other folks were convinced by the motion of the planets, by the pattern that the moon has as it orbits the Earth, that geocentrism was in fact the correct way to view the Earth and planetary systems. We're also going to talk about some original horizontality. These ideas actually date back to the 1600s, most of them. Original horizontality, superposition, lateral continuity, and then we're going to talk about Neptunism versus Plutonism, and then eventually catastrophism versus uniformitarianism. Now, these are words that mean nothing to you now, but you will know this by the end of this lecture. Unconformities also. So we're going to talk about unconformities. We're going to talk about evolution, that E word, and then also faunal selection. It's the way we understand geologic time in the stratigraphic record. And then finally, cross-cutting relationships and inclusions. So that's what we're in for. The background picture here, by the way, is from Scotland. If you ever have a chance to go to Scotland, take it. Okay, this is one of the most beautiful countries on Earth. If I were to compare it, I think there's maybe 3 other countries on Earth that would compare: New Zealand, Norway, and of course home, the United States. And I've never been to a lot of places, so there may be some other places around the world that are just as spectacular. But this is really something here. This is a valley right here. It's called Glen Tilt, and it has a long and historic past, I guess you could say. But mostly volcanic rock here, but at the same time, there are sedimentary rocks. But the reason why I include this is because so many of the earliest ideas in geology were actually from Scotsmen, early Scottish scientists, gentlemen who were studying the natural sciences. And so this is that story about how these natural sciences have contributed to the study of geology. The earliest we have the records. People always look for explanations. Let me put it this way. I've been teaching geology for a long time, right? And when you give a multiple choice exam, there's always going to be somebody who will fill in that answer, whether they know it or not, right? And that's the way it's our human nature. We look for explanations, and if we don't hear the right one that we think is appropriate, we exclude it, and it's just been human nature ever since we were around. And so there are many, many origin myths that are out there. And for the longest time, at least in the last couple of thousand years here, ideas came predominantly from the church and from the texts that were incorporated into the Bible. If you come from a Judeo-Christian sort of background. And so in Western culture, the Christian church has kind of dominated that thought from 313 AD. And the reason for that actually is this emperor. This is Emperor Constantine over here on the right-hand side. He converted to Christianity. He was a Roman emperor, and he converted to Christianity on his deathbed after he'd done all the things he needed to do in order to be emperor. And then he has forgiveness, of course, at the very end. So that dominated thought from between 313 AD, I guess, is when he adopted his viewpoint, and all the way up until the mid-15th century here. And so we're gonna talk pretty much starting with the mid-15th century then. But the church doctrine of the Middle Ages, here's what it was: that it took 6 days to create the earth, that it was 2,000 years between the creation and the Great Flood, and the Great Flood to the Christian era was another 2,000 years, and then 2,000 years of a Christian era. And then, Jesus would come back, and then there would be 1,000 years of heaven on earth, essentially, and then for the rest of eternity at some point. And they also felt that the earth was the earth was the center of the universe and not the sun. And they didn't know what the universe was back then. They didn't know what galaxies were back then. And so we're a part of one galaxy out of 200 billion. And we know now that the sun is just one of those solar systems that's going around, flying around this galaxy. It takes us 26 million years to go make one revolution around the center of the galaxy. But back then, they thought the earth was the center of everything. And of course, that's human nature to think you're the center of all things, right? And so man was God's creation, and therefore the earth was his domain, essentially. And so we've used that to our advantage, I guess, as much as you could possibly do to have dominion over the planet and over the animals and everything else that's here. And everything that is alive deserves a life, I guess you could say. But ideas began to change. In the 15th century, people began to study, and so there were clerics, and many of them were, religious folks. And so, but as they studied the natural world around them, they saw that it didn't quite jive with the historical record written in the Bible. And so one of those guys was Nikolai Copernicus, and so he adopted the name Copernicus. I can see why. And he proposed, in fact, on his deathbed, he said, I think that the sun does not revolve around the earth, but the earth revolves around the sun, and the moon revolves around the earth, or orbits the earth. And so some of the ancient Greeks had that same idea. And in fact, even the ancient Greeks, like Aristophanes, knew that the earth was round or spherical. And so some of the ancient Greeks, some of that was coming back into vogue because he had read some of these ancient manuscripts, of course. Well, he published his results like the year that he died in 1543, okay, because this was a new idea. He knew it was going to be controversial, and he probably knew that he was going to pass away at some point, but he wanted to get the idea out there. And it took a few years for it to get out, okay, so most people had ignored it, and then eventually Galileo Galilei, this guy right here, he came up and he says, you know what, I think that Copernicus was probably right. I think that the earth does orbit around the sun, and that the sun is, in space, and all of the other planets actually orbit around the sun as well. And he, as he was studying these things, he realized this was going to cause some problems for him, and it did. And he did some experiments. Of course, he was a scientist, right? He was an artist also, right? So, but he was a scientist as well, and an inventor. He invented a flying machine, for instance, and he also invented a tank, essentially. But this is the place where he did one of his experiments. That's the Leaning Tower of Pisa here. And Pisa is on kind of soft ground, and so the tower is leaned because of subsidence on one side. And so because he knew it was leaning like that, he says, you know what, I'm going to do an experiment. And he took a wooden ball and a metal ball, and he dropped it from that railing up at the top up there, and he saw which one landed first. Well, they landed at the same time. And he realized from that gravity acts the same regardless of what the density of a material is. And so you could drop something that's much lighter, as long as it doesn't have any air resistance, right? Like a feather would not go as fast as a metal ball, for instance, because of the friction from the air. But because a wooden ball and a metal ball landed at the same time, he realized that gravity existed, and then it had an attraction to these objects, and it didn't matter how large those objects were, at least the ones that he could carry up to the top. They're always going to fall at the same rate. And so he learned the gravitational constant for Earth from that. And he's regarded as the father of modern physics because of that experiment. Well, he proposed this idea, and of course, immediately he was thrown into the Inquisition, which would attempt to get him to recant his story. And of course, and he did, because that's what you do if you wanted to stay alive back then. And but it was one more generation, not very long after that Johannes Kepler proposed the same idea. And he says, you know what? Not only does the Earth orbit the sun, but also it is in an ellipse. And so that elliptical pattern we recognize even today, and we know that ellipse actually changes its shape somewhat. It was at his time that there were some very profound sort of things that were beginning to shake up the old ideas. And so the church was going through some difficulties at this time. In fact, that was the timing roughly of when Martin Luther had posted his indictments, essentially, of the church. And then And then it was also political upheaval at this time as well. And so Oliver Cromwell was a commoner in Britain and essentially overthrew the king. And they put in a more of a egalitarian sort of, well, it wasn't really, they were really elitists who were in charge in Britain at that time, but some of the nobility and so forth. And so, but eventually it was returned back to the crown with the restoration of King Charles. And so the church recognized they could no longer fight some of these ideas. And so heliocentrism was one of them they couldn't fight anymore. Helio meaning the sun, and being the center of what we know today of as the solar system. Back then, they thought that was the extent pretty much of the universe with the fixed stars in the background. So Johannes Kepler's work, he dealt with how Mars revolves around the sun, how Venus revolves around the sun, and so forth, and he recognized the pattern that they make when they go around the sun, as does the Earth, and how the moon goes around the Earth as well. As the planets go around the sun. So into this sort of framework, there was a young man who was a gifted anatomist. He would dissect animals. He very carefully drew what they were. And he was doing some of the earliest sort of work in biology by trying to understand what the tissues were and what the function was of each of the different parts, essentially, of not a human body so much as they were animals that he looked at. So, for instance, he finally, well, his father was a clockmaker, and so he had this precision with his hands. He was very precise in how he could like carve things apart and so forth. And so, but he was a scientist and a thinker, and he began to study fossils. And as he studied fossils, he realized that it's like, I'm not studying in the right place. At that time, the leading educational institution in the entire world was in the country of Tuscany, and Tuscany is a little bit north of Rome, for instance. And so this was in the 1500s. And so Niels Stinson was his name. We know him today by the name Steno. Steno is an abbreviated version of his name, but Nicholas Stenoninus, or I think it is what he actually called himself. That's what he published under anyway. And he gave us three of the very most important parts of geology. And when he studied rocks, for instance, he was doing this in Italy, in the foothills of the Alps in Tuscany. And he looked at how the layers of rocks were exposed there. And so when he studied this, and he traveled around, he's originally from Denmark and made his way to Holland, I think, was the next stop. And then on his way, he came to Italy. Well, what today is Italy, and back then it was Tuscany. And so the Dukes of Tuscany, the Medici, were the ruling family in Tuscany at that time, and they were the richest family on earth as well. Trading with the Far East would help them to develop their great wealth. And so they sponsored scientists, and so they had this academy there. And so in that academy, he studied the rocks. And so he studied things like how the rocks were laid on one another. And he reasoned this, like if you have one layer, and another layer over the top, the layer over the top has to be younger than the layer below. And that principle, even though it sounds just like common sense, it had never been written down before. He was the guy who wrote it down. And so they call that superposition. So if you have a sheet of paper and you throw it on a desk and then you throw another sheet of paper on top of that, it's superposed on top of the older sheet, right? And so in rocks, we know that would be the oldest sheet down below younger rock. And so you have older rocks are overlain by younger rocks. That's the idea of superposition. Original horizontality. He came up with this idea and he says, all of these things are made out of sediment that I see here. He was fortunate enough to be studying sedimentary rock. And so when he looked at these rocks, he says they're made out of particles. And those particles are just like I see being deposited on the beaches and along rivers. And so he recognized that rocks were originally sediments and that those sediments were originally deposited horizontally. In other words, he also was around the mountains enough to know that some rocks are vertical, but there's no way you could pile sediment up in a vertical bed and get it to retain that shape. It would fall, it would spall off and fall down and form a little cone of sediment, if you will. So in other words, you can't have rocks that are vertical. They have to be originally horizontal, or roughly horizontal anyway. And he recognized that they'll go on forever until they run up against something or they peter out somewhere. So in other words, they either disappear because there's no more sediment to disperse, or they run up against something, some sort of barrier, if you will. That's called the principle of original horizontality. The next principle that he came up with was lateral continuity, and that actually can be used in a couple of different ways. One of them is he recognized that sometimes in valleys you can see one layer of rock and it looks like the same layer of rock over here on the other side of the valley. And if that's the case, they must have been joined up at one time. There must have been some lateral continuity between them. And when you see these rocks, not only would they join up like that, maybe they go out in that direction, this direction. So it kind of lines up with this idea of original horizontality as well. That's the principle of lateral continuity. They'll go on forever until they run up against a barrier, or until and you can project where they were at one time if they've been removed by erosion. So he's a very clever guy. So he went on to write about this pretty much towards the end of his career, actually, and he wound up going back to Denmark at one point. At least he wanted to go back to Denmark. I think for his family. Actually, his father had passed away already. But anyway, he wound up publishing this, and he never got to publish some of the other ideas that he had. But anyway, I read a book on him last summer. It was a fascinating read. I think it was I can't remember what the name of the book was, but it was very good. It was all about Steno. So Steno is the guy who came up with these three principles. They're very important. So remember these, okay? Superposition, principle of lateral continuity, and then also the principle of original horizontality. So he came up with those three ideas. And three people had the heliocentric idea. That would be Copernicus, Galileo, and then also Kepler. And so when people began to study these rocks, they realized, okay, it's like, okay, well, Steno wrote about this, and I think I recognize this. There was a guy who did this, this Marsili. He was another Italian geologist, a early geologist. He did the first cross-section that we know of. And so a cross-section kind of portrays what the rocks look like in the mountainside. And that's what he shows here. Those different layers of rock that crop out in different areas here. And he's showing you what the oldest rocks are and what the youngest rocks are in this diagram here. Now, he's actually doing it along a river or a stream there, but he's showing you that they're all laid down on top of one another. And so the oldest rocks were those igneous rocks, in fact, and over the top of them, there were all these other rocks that were laid out down the valley. So here's just some definitions anyway of what superposition is. That is, younger beds overlie older strata. The principle of original horizontality, that sedimentary rocks originally were deposited in horizontal sheets, and they'll go on. And so the original, the principle of lateral continuity is that they'll go on until they either pinch out, they just disappear, or they run up against some sort of barrier. So that's the principle of lateral continuity. So all of those go together and are attributed then to Steno. So when people began to look at the rocks, they began to describe the layers of rocks, and then they had to identify what the rocks were. And so they're among the original folks who studied sedimentary rocks. It's like, this is made out of sand, and so they would have names for these things. So for instance, sometimes a conglomerate would be called a grit or something like that. In Britain, that's one of the terms that they would use for a conglomerate. Okay, well, let's go on to the next slide here, and I want to show you what original horizontality looks like. Those beds are dipping slightly there. Now, you can't hardly tell it, but they are, and they're only slightly dipping off to the right-hand side of that photograph. Now, this is a place in a that's called San Rafael Swell. You've already seen a photo of San Rafael Swell, and you got to see some sand dunes that were actually tilted there. They'd been uplifted on the San Rafael Swell. Forces from below had raised that landscape up, and this landscape has been raised up as well. And it's slightly dipping towards that canyon. So if you were to follow the canyon road, it would head out towards the mountains in the far distance out there. But these rocks were originally horizontal. There's no doubt about it, right? So that's what they are. They're relatively flat, but they've been tilted by geologic forces later. They were originally horizontal. The older rocks at the bottom, the younger rocks at the top. That's what we call superposition, right? And lateral continuity. Well, we don't see anything pinch out here, so they must go on, right? They'll go across that valley. They'll continue on. In fact, you can see the resistant ledge at the top here is repeated on the next little other side of that canyon, okay, a little bit farther to the right here. And then there are younger rocks over the top of that even. So now this is interesting because at the San Rafael Swell, the very base of the section here, the very bottom of these rocks that are exposed here, those are the same age as the rocks that are in the Grand Canyon. Now, it has a slightly different name. In the Grand Canyon, we call it the Kaibab limestone. Here it's called the black box dolomite. It's a slightly different depositional environment, but it's the same age rocks. They're Permian in age, named for a place in Russia. It's the ancient Perm kingdom, but this is, in fact, where these rocks crop out here. And it's like, well, do they go all the way down to the Grand Canyon? In fact, except where they've been punched through by igneous rocks here and there, yes, that is correct. These things go in the subsurface around this area, in fact. And so they're overlain by younger rocks, mostly in the canyon lands and places like that. And so all of those beautiful red sandstones, they were all deposited over the top of this. That's a marine deposit down here at the bottom. That's a carbonate, right? So that's the black box dolomite, overlain, in fact, by the Moenkopi Formation. So the Moenkopi Formation here has dinosaurs in it. So if that's the Permian down here, that's actually Triassic above it here. And there's fish fossils and all sorts of other sorts of fossils in there. But the rocks at the bottom of this photo predate the age of dinosaurs, and those are actually part of the age of dinosaurs, the Mesozoic here in the upper part here. And that's the Moenkopi. That's that shale that has that sort of slope to it there, because shales have a tendency to form a slope like that because, well, they're small particles, right? And they're easily weathered and eroded. And so that is that's the idea of original horizontality here. I'm going to challenge that idea now. There are places where the Navajo sandstone crops out. Now, the Navajo was one of the rock units that was cross-bedded at the top of the San Rafael Swell, where the road went into and up the canyon there. These are the same age rocks right here. In fact, these are the ones that form the flatirons along the front of the San Rafael Swell. So what you see here, in fact, is layers of sandstone. That's a quartz sandstone in here. Good thing we studied sedimentary rocks, right? These are quartz sandstones that have high angles of dip to them. But it's not really dip, actually. If you can recall, when we looked at like sand dunes earlier, you could actually see the cross-bedding in them. And in fact, that's what this is. This is cross-bedding. So how does that violate this idea of superposition, or does it violate the idea of original horizontality? Well, only a little bit. If you follow individual bedding planes across this photo here, you can see that they're relatively flat, and that just within those beds, you can see the cross-bedding then. And so if you can imagine sand dunes, which are blown by the wind, right? And so the sand grains come up to the edge, and then they'll slough off, and then they march. And so sand dunes have a tendency to actually migrate through time because they're sedimentary particles. The same thing happens in the Sahara Desert, right? All cross-bedded sands in there. And so you get this sort of cross-bedding with this. It would have looked a lot like the Sahara back during Jurassic time here. So this is slightly younger than the Moenkopi, and just absolutely stunning. So below this, it's the Kayenta Formation. We don't quite get to see the Kayenta Formation here, but beautiful rocks in here. So they're all cross-bedded sandstones. And so the relative horizontality is really not violated. It's just a type of horizontal bedding where the beds tend to march off in a certain direction. In this case, we actually can make the interpretation that we're heading to the right-hand side of that photograph. As it turns out, that's towards the north in that photograph, kind of the northwest. In the next slide, we're going to tell you about some more ideas that geologists had early on. There were some folks who thought that the entire world, all the rocks were created during the Great Flood. And that's one of the stories in the Bible that suggests that there was 40 days and 40 nights of rain, and that the ark was filled with animals and so forth, and there was a judgment on humanity. There are some people who have come along after this then and said, maybe that Great Flood was like a reminder of what happened when the Black Sea filled, when it finally breached, or maybe, it was only about 5 million years ago that even the Mediterranean finally breached, and it flooded in through the Straits of Gibraltar. And so at one time you could have walked across on dry land from Africa all the way into Europe. Can't do that anymore. And so the idea was, they call that Neptunism, that all of the rocks on Earth were formed in the oceans, essentially. And that's kind of weird, right? Because, how do you form a basalt? Well, we know that there are pilobasalts that form in the deep oceans, right? But in this case, not so much, how are you going to form a granite in the ocean? So along came somebody else with another idea, another cleric, actually. His name was Morrow. And he said, I think that all of these rocks originally were in the earth and formed as magmas. And so that idea was called Plutonism. And I've kind of pushed that a little bit in this class already, because Plutonism is this idea is like, if you're to get a sandstone, you have to have the quartz grains first. Well, where does quartz form? From magma chambers. So there had to have been a magma chamber at one point that was uplifted, weathered, and eroded, and those sand grains had to be derived from igneous rocks at some point. That's really the root of most of the detrital sedimentary rocks, is this idea of Plutonism. This is not far off, is it, right? And then other people had this idea that there must have been series of catastrophes, because whenever people began to look at the rock record, they would see these intervals where you get one type of fossil, and all of a sudden there's a completely different kind of fossil that comes along after that. So catastrophism kind of lines up with this idea of a great flood. The guy who came up with that, his name is Cuvier, a French scientist. And so we still have these ideas. And so, but at the time when these ideas were formed, it was still pretty tightly tied to church ideas. And so nobody was willing to say that, oh, no, this is not the way it works. It's like, you can't trust the Bible for an earth science textbook, okay? So I think, if you want to say, if humans were actually created in God's image, God was a thinker, in other words, and he wants us to figure these things out. This is his puzzle. So science is still bound by these ideas in some ways, but not so much in other ways. And so people have mostly discarded these things. So natural philosophy began to be applied probably in the late 1700s. So in the mid 1600s and late 1700s, people began to realize, this idea of heliocentrism, evidence supports that. Evidence supports the idea that this is the way we should view the geologic record. And then along came this idea of the Age of Enlightenment. And so, or an age of reason, if you will. And so for the longest time, it had been the divine right of kings in Europe, is what they called it. And so kings were the earthly manifestation of God's power and so forth. And the church was God's, other arm here on this planet, to get people to behave and do the right thing, right? Well, the Age of Enlightenment came along and said, you know what? You have a brain, you need to figure this out yourself. And so there were philosophical societies that began to be formed at this time in the 1700s. And so the Royal Society of London was one of the earliest ones. It's the Academy in France was formed about this time as well. And so people began to have arguments, and they began to develop this concept of what science is. Science is argument based on evidence and reason. And so that's the way that science proceeds. If you can disprove something and say, hey, it works better if we do it this way, and here's my idea. And then they would present these ideas, and people would either accept or reject them. And so the Royal Society of Edinburgh came along after this. I mentioned that because the next guy was a member of that. So as we're talking about these early ideas in geology, this guy is considered to be the father of geology, the father of modern geology anyway. His name is James Hutton, and James Hutton was a Scot. He was also a doctor by training, and he didn't like being a doctor, and so he went back to his home, which is in southern Scotland, and he tried to do some farming. So he was going to become a farmer then. But he couldn't get his mind to shut off. He would look, for instance, in the southern part of Scotland, it's, just north of Hadrian's Wall, around Hadrian's Wall. And he recognizes, like, those are Roman ruins over there. And then next to that would be these, like 1100 ruins, so like early Middle Ages sort of ruins. It's like the Roman ruins are really weathered. The Middle Ages ruins are just a little bit weathered. And of course, he was living in the late 1700s. And he also recognized that on his farm, every time it rained hard, sediment would be carried along these little rivulets and into the creeks and into the streams and then into the rivers and eventually make its way out to the ocean. So he had the opportunity to travel. And he met some really interesting people. And so they discussed these ideas. And he says, wow, erosion is really important, So this material comes from the weathering of rocks. And those rocks then get the sediments derived from those rocks. Erosion is an important issue. And so he looked at that. He also discovered at one point that there were uplifts as well. And so he discovered that, and we're going to get to that in just a minute here. But he went to Edinburgh, where he worked with other folks at the Royal Society of Edinburgh and had friends there. And they would go off and do excursions to look at some of the fossils, or they would look at some of the rocks in various places. And he recognized that those sediments that formed, that were deeply weathered, and then eventually they would be buried, lithified, and they would turn to sedimentary rock at some point. So he reasoned that the Earth must be pretty old, and it's not this 6,000-year-old sort of like orb that is being orbited by the sun. And so everybody had discarded the idea of geocentrism at that time. So I'm going to show you some areas where he visited. I have not visited this area, but this is an area called Glen Tilt. It's up in the Grampian Highlands of northern Scotland. And at Glen Tilt, the River Tilt runs through this valley. It's a deeply glaciated valley, and at the very bottom in the middle of this river, there's a waterfall. And where that waterfall comes over the rocks there, it erodes into granite and also the rocks that the granite intruded into. And he, for the first time, recognized that those rocks, the granite, cuts the other rocks here. He thought they were sedimentary rocks, but they weren't. They were actually metamorphic rocks, as it turns out. But here's the location right here. This is a Google Earth image. So I didn't have it in, and another image that I grabbed off the internet as well. But the pink areas in here are granite, and the darker gray areas in here are actually metamorphic rock. And so it's down where the circle is down here in this sort of oblique view of that valley down here. And so he recognized that granite had to intrude and had to be younger than the rocks it intruded into. Now, that doesn't stand in opposition to superposition. It just means that there's a different kind of relationships that rocks can have, that you can take younger rocks and intrude them into older rocks then. In fact, they have to intrude into older rocks, right? So that's when we talked about plutons, we talked about cross-cutting relationships then, although not in great detail. Now we're talking about that. So he looked at this and it's like, oh, I'm going to start mapping these things out. Well, when you want to describe something, the first thing you do is very carefully document what you see. So he made this map. This is one of the early geologic maps of a small area where it shows where what he thought was sedimentary rock in here being intruded by the pink in here, which is the granites that would have intruded into this rock. They were just shot through this succession here. And so that is where he looked at this granite. He knew that the granite was crystalline and that the other rocks that were around it, he thought that those were sedimentary rocks, but they're actually metamorphic rocks. We're going to talk about metamorphic rocks after this. And so that is at Glen Tilt. The next place he visited was actually in Edinburgh itself. Okay, so if you're a gentleman in Edinburgh and you go to these meetings and have your apartment here in Edinburgh, he would go for walks all the time. And so when he went for walks, he would often go to Holyrood Park. And this is Holyrood Park, which is adjacent to, it's the national capital of Scotland right here in Edinburgh. And it's a park that was owned by the King of Scotland. And so when he visited this, we've kind of talked about this, I think, previously, but I'm not sure. We talked about Salisbury Crags, I know. So we've talked about that. That's a sill, right? You guys know what a sill is now. And it's a sill that's made out of a rock called diabase, or we also called it dolerite, right? So that is the dolerite sill. You can actually see it viewed from the north here. This is actually from Nelson's column here, Nelson's monument. Lord Nelson won the Battle of Trafalgar, and they erect monuments to you if you win battles. So that's where this view is taken from. And you can see Arthur's Seat behind back here. Well, Arthur's Seat is a volcanic neck, essentially. And so most of the volcano's been eroded away. And where Salisbury Crag had intruded into these rocks, it came in and then later was tilted like this, right? And so that is Arthur's Seat, Salisbury Crag. And you get some columnar joining around here. Remember, columnar joining is what we saw at Devil's Tower, right? The claw marks from the Great Bear, right? So here, in this next photograph, you can see where the top of Arthur's Seat is. Now, this is on the opposite side of Arthur's Seat here, but right near the top, as you're going up the trail to see Arthur's Seat, there are volcanic breccias in there. And then here, you can see Nancy standing on top of some of these columnar joints here that are down farther, and so they had cooled at some point. And right at the very top of Arthur's Seat, you can actually see some other columnar joining in here, little tiny ones. So it must have cooled very, very rapidly up there. And then Salisbury Crag, you can see the sill off on the left-hand side here. So from that, he recognized that these must have been igneous rocks. Because they're associated with that volcano, they've intruded, and they're younger than the rocks that they intruded into. So that sill was actually emplaced between the sandstone at the bottom and the sandstone above it. And so that is the idea of Plutonism illustrated again. And so this idea, he's like, oh, I think that's the way it works. And this is a special type of intrusion right here called a sill. He's a very brilliant sort of thinker. Here's some more photos to show you what the landscape looks like here. This is taken from the north, this is southwest, looking at Salisbury Crags cropping out on the left-hand side and Arthur's Seat up on the right-hand side. It's shaped like a saddle, right? And so King Arthur, who's the legendary king of Britain, right? And so that's a saddle that he would have ridden his horse on. Salisbury Crag again here again. And then also you can see here, that's me actually with the red backpack on the at the top of the Salisbury Crags there. And so this is an area you can walk the trail around here, and it winds up down in the city here in Holyrood Park. All of that's part of Holyrood Park. And then this is part of the old part of Edinburgh here, near the palace for the King and Queen of Scotland. Of course, that's passed into the hands of the British monarch now, right? So they call it the United Kingdom now. So it's the United Kingdom of England and Wales and Scotland. Actually, they leave out the Welsh part there. So for Hutton's section, that's along Salisbury Crags here. He actually illustrated that as well. And when he did that, he showed that the sandstone had to be older than the rocks that intruded around it. And you get that idea when you see, so if that's the sign that illustrates when people are seeing this, here you can see actually the sandstone has been upwarped slightly, and the diabase sill or the dolerite sill has been emplaced around it and actually partially underneath of it. And so that is the Salisbury Crags. They're up close and personal. So Nancy's got her hand on the dolerite there and the sandstone down here below. Okay, this is probably, and the next one, this is another one of Hutton's great discoveries. So if he's already discovered that rocks originally were igneous, and that the igneous rocks can be weathered and eroded and deposited and become sedimentary rocks, he's discovered already 3 parts of the 4 parts of the rock cycle. This is where he put a large part of the picture together. And it's a new concept, too. And it's the one that proved to him, anyway, that it didn't prove, it illustrated to him that the Earth is absolutely ancient in age. And so this is a place called Sicker Point. So Sicker Point is along the Berkshire coast of Scotland, in the southern part of Scotland, a little bit south and east of Edinburgh. And these photographs don't do it any justice, but it's absolutely astonishing. When you go down this slope, there's a rope that you can hang on to, and there are little tiny places where you can put your feet in. Hopefully you don't wind up in a heap at the bottom, but it's very slippery along there, and you have to travel through a pen that's full of cows and bulls and so forth, right? And so I think we almost started to stampede when we were there because you could see the cows turning circles around, but eventually they wandered off. We tried to stick as close as we could to the fences just in case we had to jump over them. But here we are. We're making our way down the slope and looking down at Sicker Point here. So that is Sicker Point. And there's a little smuggler cave right to the right-hand side there. So that's in the panorama at the top. He discovered there what they call an angular unconformity at Sicker Point. And so James Hutton here at Sicker Point, he and John Playfair and James Hall, two of his friends, hired a boat to take them along the coast of Scotland because he had predicted that this thing would have occurred because he had seen it elsewhere in Scotland. He says, I think we can find these rocks along the coastline of Scotland. And of course, it's not the common place that most people go, right? Fishermen and people that are sailing along the coastline, but nobody stops along here, right? Except for the smugglers. And so he came along here, and then they saw this unconformity, and they said, we got to pull in here. And so they beached the boat down here, pulled in, and spent the better part of a day here. And so you can see the boat down here at the bottom, a sailboat, right? And so he and the crew and his two friends, and they came out and they saw this feature right here that Nancy is pointing to. Now I'm going to show you some movies of this as well, so I have to splice those in. I'll show you those in a minute here. But what you see in this photograph here are rocks that originally were horizontal. They've been slightly tilted now, but they cut rocks that are actually vertical. And where they cut those rocks that are vertical, well, I mean, Hutton had read about, original horizontality already. He says they couldn't have been deposited that way. They've been brought to this upright orientation by the fact that there have been some huge upheaval, right? And then they were cut by erosion afterwards, and these other rocks were laying over the top. Absolutely a sacred spot for geologists. And it's, I didn't find a bit of trash here. Nobody had visited this place for maybe a few days. But anyway, it's actually kind of, nice to see a place that is so, I guess, well kept and available for people who want to visit it. Here's the story of what happened here. Originally, the rocks were laid down horizontally, right? And then there was some sort of mountain building event that made those rocks be folded. And so as they got folded, they got pushed together essentially and folded into these sort of up and down sort of valleys. Now you're going to learn enough geology. You're going to know that those are anticlines and synclines here at the end of this course. And so the forces have bent those rocks into these folds like this. And then eventually weathering took place. This would have been in a mountain range perhaps. And that mountain range was kind of beveled by erosion. Streams and all sorts of, eons of time have passed over and eroded that. But then eventually there was a sandstone that was deposited over the top of that. So the beds below are sort of like a mudstone. They call it the Gala mudstone. And they're Silurian in age, actually. And these rocks over the top, the sandstone that's over the top, that's Devonian in age, in fact. And so there was an uplift, and those rocks were deposited over the top. And then afterwards they were tilted, and then they were eroded slightly. And so, but some of them are still there, right? And so that's what you see in the photographs here. So here's me at the same place where Nancy was here, pointing towards that unconformity. Vertical beds down below, and roughly horizontal or slightly dipping beds at the top up there, up above my hand. And so just an amazing sort of landscape. And here I am standing on the right-hand side. You can see the more or less horizontal sandstones off to the right in the right-hand photograph here. And then you can see the vertical beds that I'm standing on here that are part of the Gala mudstone there. And so these rocks that are over here that are dipping that sandstone, it's called the Old Red Sandstone. Obviously, it's a red color, right? But the Old Red Sandstone is absolutely famous in England. And so they build castles out of it. They build lots of buildings. I mean, you can't go through Scotland for a mile without seeing some sort of rock structure because there's that many rocks in Scotland. And so he came up with that idea. It's like, that's called an angular unconformity now. And he realized that there must be an immense amount of time that would have passed in order to deform those rocks expose them, uplift them, erode them, and deposit other rocks over the top, and then erode those rocks, right? And so he's considered to be the father of modern geology. He has this sort of like statement that he made. It says, there's no vestige of a beginning and no prospect of an end. He thought, in fact, that there was no beginning to the Earth. Today we know there is. It was 4.56 billion years ago, but it was still a long time ago. But there is a possible end to Earth as well, and that's going to be maybe 5 billion years in the future, let's hope anyway. And that's when the sun finally gets large enough to make it out to meet Earth and destroy the Earth at some point, when the Earth, when the sun finally goes into a giant phase of being a solar body. But that's still a long time away from now, right? He used nature to lead him to these hypotheses and ultimately his ideas, and he published those in a tract, actually. It's a very short little document he called The Theory of Earth. And it took his good friend, John Playfair, to come along, and he says, man, you're a really brilliant scientist, but man, are you a bad writer? And he rewrote Hutton's ideas of the theory of Earth. And so that is what became a very popular book amongst the earliest geologists, and every budding geologist would have a copy of that. And so this was back in the late 1700s. I think it was 1785 when he presented these ideas to the Fellows of the Royal Society of Edinburgh. And so he didn't call upon special circumstances. In other words, he didn't say that there were some miracles, that snap your fingers and these things became mountains and then they were eroded. And this is a process that he developed this idea, and he called it Uniformitarianism. The same processes that operate today are the ones that operated in the geologic past. So in other words, erosion that you see, the sands, how they accumulated, all of these things happen naturally. We're not going to call upon miracles or anything like that in order to make these things. And the password or the catchphrase that goes along with that idea that the processes that operate today are the same as the ones of geologic past, the catchword for uniformitarianism, catchphrase, the present is the key to the past. So in other words, the modern analogs are how we look at the ancient rocks. He came up with that. So, that's why he's considered to be the father of modern geology. And he knew from just looking at those folded strata, the ones that were upright, the Earth must be absolutely ancient. So he gave us this concept. It's called, today we call it deep time. And deep time means that when geologists talk about a short period of time, we may be talking about 100 million years or something like that. Much longer than a human lifespan, obviously. Those are things that we comprehend very easily. But we have a hard time when we think about millions of years sometimes. Not so much in geology. In fact, I like to say that, I teach a course in historical geology, and I said, by the end of this, you're going to see that I'm going to turn you into a time traveler, and you can look back in the ancient past by looking at the rocks that surround us today, which is just there's so much power in that. It's like, so you learn how to interpret what the rocks are telling you. That is the beauty, and that's my passion in geology, is like to solve the problems that we see, whether it has to do with things that affect humans, like, for instance, how do contaminants get spread across the landscape? Where do they go? How do contaminants move in karst terrains, in caves and things like that, like around Springfield? Or were there times in the past where we don't have a good analog for it, and we do sometimes, like the extinction of the dinosaurs? Nobody had thought that meteorites could actually strike the Earth and cause massive extinctions, but yet we know that they did. And so that's kind of the interesting parts of geology. It's the thing that grabs a hold of you and makes you want to figure these things out. So that's James Hutton, the father of modern geology there. you've just seen one type of unconformity. Now, an unconformity indicates that there is missing time. So right at the bottom of that sandstone, right at the bottom of the old red sandstone, that's an unconformity right there. That surface that runs along there at the top of the Gala mudstone, right? That's called an angular unconformity because there's angular discordance. Now, you know the term discordance now, right? And concordance as well. Concordance are where things are like stacked up and in order. But discordance means they've been cut. They've been chopped off, essentially, right? So if the rocks are vertical and there are rocks over the top, that's angular discordance. It doesn't have to be that obvious. You know, they don't have to be vertical. It may be just a slight angle that they make. But that's what we call angular discordance. And that is an angular unconformity. In an angular unconformity, we know that the strata below had to have been uplifted and eroded. For the other ones, we also know that there's some ways that we can interpret them as well. You've already seen a nonconformity where that granite, we looked at this in this sedimentary rock succession there. There was a granite that was overlain by sandstone and shale, right? In Colorado, in western Colorado. In that one, that's a nonconformity because we know that those granites had to have cooled deep inside of the earth and then at some point have been uplifted. And when they were uplifted, they were truncated by erosion. And then these other rocks were deposited over the top. And so that's called a nonconformity. So anytime you have sedimentary rocks over igneous or metamorphic rocks, that's a nonconformity. I'm going to say it one more time. Any surface, okay, so a nonconformity is a surface where sedimentary rocks overlie crystalline basement rocks or igneous rocks or metamorphic rocks. That's a nonconformity. An angular unconformity is where sedimentary rocks overlay other rocks with angular discordance. A disconformity, the third variety of unconformity, is where you have no angular discordance, but yet you still see that there's a surface of erosion in the rocks below, and they've been overlain then by other rocks, and so that's a disconformity. And in that one, we're not so sure. We know that there's missing time, but we have no evidence necessarily for uplift. There may have been gentle uplift, but there's definitely missing time with every one of these. And then lastly, sometimes we see those sort of surfaces where there's no evidence for erosion, and yet we know there's time missing there because we're missing faunal zones. We're missing fossils in the record at that location because there are much younger rocks overlying older rocks, and we can only prove it by looking at the fossils that are included in the rocks above and below. And so that's called a paraconformity or a cross-conformity. And so paraconformities, disconformities, nonconformities, angular unconformities, those are all test sort of ideas. And so you're going to get probably three of those anyway on the next exam when you see it here. Okay, so here's another example of an angular unconformity. It's in Grand Canyon again. Those are Precambrian rocks down below. They're older than the Cambrian rocks. Why do we know that? Because the Cambrian rocks overlie them with angular discordance. And so the ones that are tilted here, those are Precambrian. The ones that are not tilted here, as you trace it along here, those are ones, that's the base of the Cambrian there. And so you can actually see there's a little sandstone that follows along there. It's called the Tapete sandstone. And it kind of follows over the top of what it would have been a mountain range back then. But then the whole thing was uplifted, and then it settled back down, and then seas came in and came across and cut those rocks with angular discordance. They call that the Great Unconformity. It's one of the most significant unconformities in geologic time. So when we look at the base of the Cambrian, it's the Great Unconformity. No matter where you look at it, we call it the Great Unconformity at the base of the Cambrian. Okay, do we have unconformities in Missouri? You bet we do. Here's one right here that's a disconformity, and you can actually see the angular, there's a little tiny bit of angular discordance there, but not a lot. And so that's where the arrow is pointing here. A couple of former students here in this. So this is up around Truman Reservoir. And here, the rocks that are down below are Ordovician in age, and the rocks above are Mississippian in age. And we're missing about 100 million years there, right at that surface. So there is a record of missing time there. And we're missing rock layers as well. the rocks that would represent the upper part of the Ordovician, the rocks that would represent the Silurian and the Devonian. They're all gone there. They've been removed by erosion. So that is a very important surface there. That's a disconformity. When you look at the next one, that's a nonconformity. And I think you've seen this photograph also already. This is the Tomsock power generation unit right here. And that is a rhyolite down below. But over the top of that rhyolite, there are sedimentary rocks that were deposited on top of it. And you can kind of see them dipping. And the reason they're dipping there is not because so much that they've been uplifted, but because they're over the top of a really hard rock. And so these may have had a little bit of topography as well over the top of that unconformity. In many places, you don't see that sort of relief. But in fact, that is a nonconformity right there. It's not an angular disconformity because there's no angular discordance with the rocks below. So that's a nonconformity. Anytime you have sedimentary rocks deposited over igneous or metamorphic rocks, and it's not an intrusion, that is a nonconformity. So that takes us to the point where I'm going to break off here, and we'll talk some more about these key geologic principles next. And we'll continue on with this presentation on slide 30 here. And anyway, thanks for your attention. This is exciting stuff for me. Sorry, it's like this. I get excited when I talk about unconformities and the passion that these old geologists, I feel like I've still got a piece of that anyway in me trying to figure out these problems. So anyway, I'll talk to you soon. Thanks. Bye now.